All right, everybody, let's get started. Okay. So first things first, I need to have the homeworks right here. So everybody that's turning one in should turn one in. Brandon, you have one?
Yes.
All right, and then the second thing is all your phones need to be put away and your laptops. Okay? Is that all right? And then the third thing we'll talk about is just right up here are the announcements. So, homework number 2 is due on Wednesday, not Monday. So you have a week and a half to do that. First lab's going to be tomorrow on Tuesday, so be ready and on time for that. Remember, we're going to have our dress code enforced tomorrow. So long pants, closed-toe shoes, and nothing too crazy and flamboyant. Okay, and then the reading assignment is chapter 1 and 2 in the book. All right. The other thing I will mention is that we're going to try and get these graded, hopefully by Friday, so you get an idea. But they'll definitely be in like some kind of box in the undergraduate lounge on Tuesday. Okay, so you should expect these on Tuesday. Best thing to do is pick yours up, take a look where you got points off or how you did. And then make sure that you address those points for the next homework. Okay?
Are you going to post solutions over there?
Yeah, we'll post solutions. I've really had a hard time. I posted them in the lounge in a 3-ring notebook, and they just don't seem to survive there. So I'm trying to think what I could do. Anyway, what? Scan them, email them to everybody. Yeah, that's probably just as good. I just kind of feel like, yeah, okay, so we'll work on that, but you'll definitely have access to the solutions, okay? And I asked the TA not to write a whole dissertation on your homework, but to kind of give you some notes, whether it be math or wrong approach or wrong constant. Yes?
Google Docs is good too.
Google Docs?
Sending it out.
Uh-huh.
Just kind of share a document on Google Docs as well. Email
Okay, all right. I'll look into that too. All right. So last time we left our class last time with some bad news, right? It turned out that as much as we love separable equations, most process control problems you're not going to be able to solve the problem with separable equations. So typically, what you have is multiple differential equations, and they share variables, independent variables, and really there's no way to solve explicitly for the individual variables, separate them on one side, and then integrate from some starting time to a final time. So it turned out that that's where we left off. And what I did was I made a real bold prediction, and I tried to kind of make us feel a little bit better at the end of the class and say, hey, there's an easy system for solving these kinds of problems. Okay, it's actually pretty cookie cutter in the way that you approach it. You basically follow those 4 steps that are on the course pack, and then it's real simple. You use tables. There's not a lot of memorization, and it seems to be pretty logical. So there's a nice approach to that, and we'll get to that. Not this lecture, but probably the following lecture. Anybody have any questions about what we went over last week? Just kind of knocking the rust off and doing separable differential equations. Okay? So what we're going to do now is we're going to talk about dynamic modeling. All right? And like I said, this is a cool class because you don't have to assume everything's at steady state. This is the one class that really focuses on how changes are made. Okay? And if you think about it, steady state is an important part of a paper mill, but actually dynamic things that change are just as important, And this is the first class. You've had, I don't know, how many classes have you had? Probably 30 classes up to this point, or 25 classes up to this point. And in every class, I'm not talking about English or anything. The teacher comes up and says, let's assume steady state. So this one and differential equations, obviously in math, are the 2 that really focus on dynamics. Okay. So we talk about dynamic modeling. Other people call it transient. So transient is also a synonym for dynamic. And what it says is it's just transient, is it changing with time. So if something is transient, we talk about transient people. That means that they're moving from location to location. They don't have a steady place to live or to stay. Okay? So what happens when we have a process that we're going to model and we're going to use mathematics, what it turns out is that at steady state, with this transient process, what happens is the derivatives, the time derivatives, are not equal to 0. Okay? In other words, this variable x is changing with respect to time. It might be going up or going down. Okay? But if it's a transient process, there's some derivative that is not always equal to 0. Okay? Okay, so then we come to the principle of conservation of S. Okay, and you've probably all seen this before because you've all taken 205 or other chemical engineering classes, or even Dr. Jamil's 360 or my 355 class. Okay, and what we're going to do is we're just going to basically be an accountant. So what we're going to do is we're going to say this S material, whatever it is, we're going to keep track of it within a system boundary. Okay, so if you look here, S could be total mass, it could be mass of an individual component, total energy or momentum. All right, we're going to focus on the top 3. That's typically what we do as paper science engineers, control those 3 things in a system. All right, so here's your big equation that's important. What it says is that the accumulation of S with respect to time is equal to the flow of S in minus the flow of S out plus the amount of S generated and minus the amount of S consumed. Okay? And not all of these terms are present for all of these different balances, and they're not always present for every system. Okay? So let's quickly go over the first one, total mass balance. So in this case right here, we're going to have a control boundary, and typically we're going to be working with tanks, and so we're going to put a boundary right here and define our boundary like this. Okay? So that's going to be our system boundary. And we're going to do accounting on total mass inside that system. Okay? So what we are going to do is we're going to allow the volume of that tank to increase or decrease based on whether more is coming in or more is going out. So that volume right there, that can increase or decrease. Okay? And our system boundary will expand to contain all of the material that's contained in the tank. Okay? So that's our system boundary. And then here's our balance. So dm dt, that's the accumulation of m, total mass in our system, accumulation of m, is going to equal d. Now, we're going to break total mass into rho times volume. So density times volume. Okay? So that will be nice for us and convenient because typically what we're going to do is we're going to track the volume of this liquid or the height of the liquid. More often it's going to be the height. So we're going to change that to density times volume, and those have units of mass. And that's equal to the summation of all the flows in, F sub I, times their densities. So F is in volume per time, and density, of course, is mass per volume. Okay? And we have in and out. So if the in terms are greater than the out terms, then dm dt is positive, and we have an increasing mass in our system, an accumulation. And if the out terms in sum are greater than the in terms, then we'll have a depletion of total mass in our system. And dm dt will be negative, and we'll be losing net mass in our system. Okay? Anybody have a question about that equation? It's a pretty simple equation, but we use it quite a bit in this class in order to demonstrate the dynamics of tank height, really. Okay. All right, and then we can go further. Down here, it talks about the total volume of the tank equaling A times H, right? Where A is the cross-sectional area of the tank and H is the height of the tank. Okay, and typically we work with constant cross-sectional area tanks. That might not always be the case, But typically what we say is A is equal to a constant. Okay? All right. And then what you also notice is those the generation term and the consumption term are 0 because total mass cannot be created or destroyed. Okay? So we'll use these terms for reactions, but they don't come into play for total mass. Okay? So this is one of those equations that you should get used to and familiar with. All right? Okay. So now let's go on to the second one. In case 2, we're not doing total mass, but we're doing mass balance on some component in our system. So in this case, it's some arbitrary component A. And again, what you want to do is draw a system boundary. So we've got our system boundary here. And really all the flows in and the flows out have to cross that system boundary. That's important. And now what we're going to do is we're going to do a mole balance. So N sub A is the number of moles of species A. It could be carbon dioxide, it could be water, it could be oxygen, it could be any kind of molecule. And then dt. And then we can break that down into the number of moles is equal to the concentration of A in moles per volume times the total volume. Okay? So that's just another way to write N sub A. And we can also do mass balance on like kilograms of A or parts of A too. But really in the strictest definition, the simplest way to think about it to start off with is Ca is molar concentration. But there are other kinds of concentration we can use too. But molar concentration is important because if we have some reaction and some stoichiometry we know, then molar concentration is very useful. All right, so now we've got terms like this. This is the flow in of A crossing the boundary. Okay. And then J's are the outs, so that's the flow outs of all the A's out of our system. And then we have this term RAV, which is the reaction rate per volume times the total volume. Okay? So if you look at all of these terms, every single one of them, they're all going to have units. What are the units in that equation? Anybody? Moles per time, that's right. So all of these expressions have moles per time. That's what the units are. So that's a good check. So a lot of times you can be going along through a math problem and there's all these variables flying around and you want to just check to see if you're okay or if you're off. Then what you can do is just check the units on all your expressions. And that's a good way to just make sure that you're going correctly. So R sub A, we're not going to really get into it. I'll give you the expression for R sub A, but I think most of you have been exposed to some reaction rate expressions where R sub A, it could be that the amount that's consumed or generated is proportional to the concentration to the first power or the second power, or have some other type of reaction rate expression. But I will give you those, and they will typically be where the reaction rate is some function of the concentration of the tank, of A in the tank. Okay? So then I put down at the bottom, if V is constant, the volume is constant, then dCA V dt is equal to what? What simplification can we make?
Full V up front?
Yep. Yes. You can factor out V because it's a constant, right? So if V is a constant, you can factor it out, and then we have a derivative of one single variable. This is what we like. I'm not going to ask you to solve an expression like this where both CA and V, both variables, are changing with time. You're going to find one variable that's the one of interest that we're looking at, and all the other ones are going to be constant. So that's right. So we can do that. So that's that. Okay. Any questions about this equation? Let me ask you this. Okay. how can V be constant? What are the two cases where the volume is constant? What are the two most obvious practical cases in real life where you could say, yep, the volume is constant? There's two of them. Say that again? When the flow in is equal to the flow out, that's right, that's when the volume can be constant. So flow in has to equal flow out, right? And what are the two cases where the flow in is most likely to be the same as the flow out? Actually, there could be three. Let's just say three cases. But, okay, so you have a tank out in the middle, and somebody says the volume is constant. The liquid level always stays the same. What are the three scenarios? How can that be true in real life?
You have a batch process, so nothing's coming in or leaving. So like during the batch.
Dang, you got another one, even a fourth one. Okay, so 4, you could say a batch process. That's not really the important one that I was thinking about. Batch process, so flow in equals flow out equals 0. Yep, that's okay. That's right. What are the other three? I mean, how in the world could a tank have constant volume, liquid volume inside it? Tank or vessel, I'll say.
The tank's been taken out of the sequence temporarily?
No, that's kind of like, you guys are good. Good. I mean, you're right. That's true. That's true. But there are some pretty simple assumptions that we can make about the tank.
If it's full.
It is full, yes. So you can say it's in the overflow condition, okay? So when it's in the overflow condition, or full, right? When you throw more mass in there, you're going to push out the equal amount, right? So it'll always have, the total volume will always be constant there. So overflow condition, full. What's another scenario?
Maybe like when there's a reaction, but it's not changing like the volume, I guess.
Yeah, but that could be the batch process, right? That could be the.
Well, if you have the same flow rate coming in and out, and you have a reaction, but it's not like creating something that's more, I guess it'd be a larger flow volume than something else.
Mm-hmm.
Change the overall volume.
Okay. Maybe there's not so many. Let's just say, let's scratch number 3. 2 would be
Automatic control. Flow control. Automatic control.
yep, flow control in and out set equal. Okay. So you have pumps. So you could have a scenario where there's a pump on the inlet, pump on the outlet, and then there's a flow control loop, and it's controlling those flows to be exactly the same. So that would be a good one. So those 3 actually are pretty good. 1, 2, and I'll change that to 3. The other one I was thinking about was, what if you had a closed container and you were pushing liquid in and the same amount had to come out? So it wouldn't be in an overflow, but it would be like a plug flow scenario. So let's just put kind of like a, so I guess we could put that one down 4. So you have some kind of plug flow scenario where, it's not in an overflow condition, but it's kind of like there's an inlet and an outlet, and when you push something on the in, it pushes the same amount out. So pushing volume in pushes equal amount out. Okay, so we've got basically 4. And actually, I might have misled you all. I got on this volume conversation, but it doesn't really have anything to do with the reaction part of it. It's just kind of like, let's just kind of talk about how could that volume be constant. But it doesn't necessarily have to deal with the reaction. All right, the last one that's most complicated is total energy balance. Okay, and total energy balance, this equation is always true right here. So for any system, you can use this balance right here, and that will be true. Now what we're going to typically do is we're going to work with tanks that have constant volumes of liquid in them. All right? It's not always the case, but for this class, we can kind of demonstrate all the concepts we need by, again, just taking a tank with liquid in it and making our system boundary, and then doing our energy balance around that boundary. Okay? So basically now what you've got is you've got the total energy, so capital E is the total energy of the system. That would be this volume right here. That's going to equal the internal energy, the kinetic energy, and the potential energy of this volume of liquid right here. Okay? Now, let's just see here. Typically, we ignore the kinetic and potential energy in this class. Okay? So the kinetic energy, K, would be how much energy that fluid has because it's like swirling around and spinning. Okay? And if we cared about like slowing down that fluid and harnessing that power and generating something from that spinning liquid, then we would have to track K. But in this case right here, we really don't have to track the kinetic energy. That K term comes in a lot when you have things like a waterfall, right? And you have the water falling down, losing potential energy, gaining kinetic energy, and then that's transformed to something. And then P is the potential energy of this liquid. Now, we're just going to basically say that that's going to be somewhat negligible and not of interest to us in this balance, okay? So if we were going to drop this tank from a very high height to another height and somehow harness the energy, then we will be interested in its potential energy. But right here, we're not really that interested. So the K and the P terms are going to go away, all right? And so what we have here is we've got one term for enthalpy entering the system. So little h is enthalpy, which is just the measure of energy in a flowing stream per some kilograms per mass. This is the energy out. Okay, so sum all the flows of energy out. And then Q is the heat that crosses the system boundary, and WS is the shaft work that crosses the system boundary. And for both of these terms right here, Q and WS, we're going to use the following. If energy flows into the system, we're going to call it positive. If energy flows out of the system, we're going to call it negative. Okay? And it doesn't matter whether it's Q or shaft work. We're just going to use that sign convention for both of those terms. Okay? So what you're going to have to do when you're solving a problem, you're going to have to figure out, is the heat flowing from the environment into our system, or is it flowing from the system to our environment? Okay? So how do you know if heat is flowing from the system to the environment, or from the environment to the system? What's the simple rule that you know how heat flows?
It's getting colder, it's going into the system. It's getting colder, it's going out of the system.
Okay, that what you said was very confusing to me, but basically the simple thing is heat flows from hot to cold. Okay? So that's all we need to remember for that. And then for the shaft work, you just have to kind of use your practical sense about, are we harnessing mechanical shaft work to generate electricity, or is electricity going in there to do something else, or whatever. Okay? But heat flows from hot to cold, okay? And that will give you at least the sign for Q. And all right, so typically we look at systems of tanks containing constant density liquids. And that's a nice assumption, because what that allows us to do is say that the internal energy of our system is approximately equal to our internal enthalpy. And so du dt is approximately equal to dH dt. That's true for an incompressible liquid. And that allows us to use heat capacity data and enthalpy data from charts. Okay? And that's very convenient. That's a lot more accessible than internal energy and heat capacity at a constant volume. So C sub P is the heat capacity at a constant pressure. Okay? All right. So then what you have to do is just kind of reach back to your 205 days, good memories. Total enthalpy is the total mass of the material, that's rho times V times the heat capacity times T minus a T reference. Okay? And then the enthalpy per mass of a liquid, and then we'll use this for the flows in and flows out. That's just going to be the heat capacity times T minus T reference. Okay? Typically, C sub P is little c sub p. I have capital C sub P. Don't let that get you confused. And actually, we will often set Tref equal to what? What do you think we should set it to? What's the reference temperature? Should it be room temperature? 70 degrees Fahrenheit? 25 degrees centigrade? This is a trick question. We don't want to set the reference temperature to room temperature. We'll just set it to 0 degrees Celsius. Okay, that'll work out nice for us. If we can do everything in Celsius and we can set our reference temperature equal to 0, one of those terms goes away. And that makes the math a lot easier for us. And we're all about getting to easy math equations that we can solve, okay? I tricked you. Okay. And also dk dt is equal to 0. Yeah, if fluid motion is not of interest, and then if the potential energy doesn't change with time, if potential energy is not of interest, another way of putting it is if the total tank does not move. Okay, that's another way of making that term equal to 0, and that would be the same thing for the potential energy. Okay, so we can say, if we don't care about kinetic or potential energy, or if the total tank doesn't really move, then the kinetic and the potential energies, they don't change with time. We don't track them at least. Okay. All right. So now we've got a bunch of assumptions, right? We've got that and that. We've got our reference temperature equal to 0 most of the time. And then we've got our enthalpies right here, and we've got that assumption right there. So we go to the next page, and we find an equation that we can use to solve some problems in the class. And so this is right here. That term right there is the total energy. Okay, as we've defined it with all our assumptions. And then this is the energy in, the energy out, and then we have our heat and our shaft work term. Okay. Now, if there's no phase change for the fluid, okay, so if there's no phase change, what that means is that HI is equal to CPI TI minus T reference. So then we can take that H sub I and we can replace it with a heat capacity, which we can assume is a constant, or if we get really crazy about it, we could say heat capacity is a weak function of the temperature. So we won't do that in this class. So we can have the heat capacity that's typically assumed to be a constant times this Ti minus T reference. And the same thing here for this. So H sub j turns into this term right here. Okay. All right. So what are all the units for this equation? Somebody different. Somebody different than Michelle. Is that right?
We could do it in calories or joules or...
Okay. Yep. So what are those? Those are units of energy, right? So it's energy per time. Okay? So in calories or joules are an example of units of energy. And then we could do it per second, per hour, per minute, whatever is convenient. All right? So let me see. Give examples of a non-zero Q term. Okay. Can you think of 3? Whoa, we had a hard time thinking about 3 ways to make volume constant. This should probably be easier, right? So what are 3 examples of a non-zero Q term?
If you're having a reaction that releases heat, so like if you're turning hydrogen and oxygen into water, that releases a lot of heat. Okay. Now, remember that Q term, for it to be non-zero, there has to be some heat that crosses that system boundary. So in itself, you could have a reaction,
But if all that energy stays within the liquid and none of it crosses the boundary, you would still say that Q term would be equal to 0. So your explanation, although you're on target, when things heat up, there are heat flows. I can't say that's correct just the way you said it. Let's try to reword it a little bit differently. You're on the right track.
You can tank with a cooling coil inside of it.
Exactly. Okay. So you can say, let's say a cooling coil removes energy. Okay. Okay. And then I heard something else that I liked.
If you're not insulated,
Okay. So what's that going to do?
you're going to release heat.
Okay. So all right.
Or
So
absorb heat if it's hot outside. Or absorb heat if it's
yep,
hotter outside.
that's right. So you can have heat cross the boundary from a simple temperature difference and the system is not insulated. What is the technical term that us scientists and engineers call that type of system? Adiabatic. Adiabatic. So if it is insulated, if the system is not insulated, okay, so that's going to be non-adiabatic. Okay. So if you recognize that there's a temperature difference between your system and the surroundings, and you have reason to believe that it's not perfectly insulated, then you have a non-adiabatic situation, and you can have heat go into the system or out of the system, right? So we've got a cooling coil, that's 1. Heat crossing the boundary because of a temperature difference, that's 2. And then the third one, it's kind of the opposite of the cooling coil.
If you're utilizing the heat to like boil water into steam or heat some other products.
Okay, so how does it happen?
So maybe you have a pump running tank where you pump the contents out and it goes to the exchanger with another stream of
Okay.
water.
Okay. So that's almost this delta T part where you've got some hot fluid. So I think what you're referring to, if you have an indirect heat exchanger and you're pumping it out to another place and it's contacting a piece of metal where there's another temperature fluid on the other side, that I think would be this 2 right here. The other one's just the opposite of this cooling coil. It's just like a heating coil. For instance, electrical resistance heater to heat a gas or a liquid. Okay. So all these cases, if Q does not equal 0, then we call the system non-adiabatic. Q equals 0, for one reason or another, we have an adiabatic system. Okay, so you have to look in the problems that I assign and make sure that you look for some of these words that are clues. Okay, clue words. Okay, so we did that. All right, so now let's do a example problem, and this is very much like this is like a combination of 2 homework problems that I'm giving you. Homework problem number 6 and 7. If I can find it. Somebody steal homework number 2? I hit it on myself. Thank you. Thank you. Yeah. So I've got a problem number 6 and a problem number 7, and they're actually they combine the concepts that are actually in here. So we're good. All right. Okay. So we've got a dynamic modeling example. The first thing to do is read the problem, have a little bit, just kind of sit back and look for clues to tell you which kind of balance you're going to need. Remember, I talked about the balances in this class will be usually total mass, component A, and energy. Okay? So let's look at it. We've got a 4,000 milliliter tank. So that's actually pretty small, 4,000 milliliters. Yeah, that's like that's a graduated cylinder. I don't even know if you can call that a tank, can you? All right, 4,000 milliliter graduated cylinder is initially filled with water at 20 degrees Celsius. Okay, so I see that 20 degrees Celsius, and that could be a hint that it's an energy balance, or I might just be giving you that because you might have to look up the density or the heat capacity or something like that. So don't jump to conclusions, but there's a temperature, and usually that means energy. At time equals 0, the input to the tank is 2,000 milliliters per hour of water at 40 degrees Celsius. What is the temperature as a function of time? Okay, so if we're looking at temperatures versus time, the things that change temperatures are energy flows in and out, right? So basically, when I see something like that, I'm thinking a total, an energy balance, okay? I've seen temperatures versus time. I'm thinking about my energy balance. So, first thing I will do is I will draw a picture of the system. So we've got a 4,000 milliliter tank. Okay? And I'm going to draw my tank like this. Okay? And the reason why is because this thing right here indicates that it's in overflow. So if I add one more drop of liquid back in here, we'll have some flow out over that overflow. Okay? And then that thing right there is a stir. And that symbolizes that everything is very well mixed inside. So we don't have to worry about hot spots or cold spots or things like that. Okay, so then what I'm going to do is I'm going to label my diagram. So I'm going to say my volume equals 4,000 milliliters. I'm going to also say, I wish I drew a bigger diagram because I would prefer to put it inside. But I'm just going to say here that the temperature is initially filled with water at 20 degrees Celsius. So I'm going to say Ti at time equals 0 is equal to 20 degrees Celsius. Okay? So now I know the total volume, and I've labeled that the initial temperature at time equals 0 is 20 degrees Celsius. At time equals 0, the input to the tank is 2,000 milliliters per hour. So I'm going to call this flow in. That's going to be equal to 2,000 milliliters per hour. And then I'm going to say that Tn equals 40 degrees Celsius. All right? And then flow out here, I'll call it flow J. Should I call it J or O? I'll call it J. Flow, no, I'll say out. Flow O is, what is that equal to?
2,000 milliliters.
Yep, because we have 2,000 milliliters, because we have it in an overflow condition, 2,000 milliliters per hour. And then the temperature of the material coming out. Now, what variable should I use for that? Say that louder, please.
Is that what the T of T is that we're trying to find?
Yep. So that's the T of T that we're trying to find. Okay? And we're going to use that as our variable. It's important to use this as our variable because that's what I ask for. Now, what's the temperature inside the tank? It's the same thing. Somebody said it's the same thing. That's right. If everything is well mixed, if we're using that well mixed assumption, what that means is that the flow out is going to have the exact same properties as every little packet of fluid inside the tank. Okay? That's an assumption of perfect mixing. So a lot of times people kind of get confused about that, and they'll say, oh, I need another variable, T sub tank. Okay, and then they'll have T sub tank and T outlet, and that to me is that's a problem. That will cause you some significant problem. So basically, what I want to do, just to remind ourselves of all this, is I'm going to put that variable right inside that tank too. Okay, and that reminds me that those two temperatures are the same. It's very simple for people to just put T sub O here, but we don't really need T sub O. If this is going to be the temperature of our tank coming out, that's the temperature. Yeah, I mean, we just don't put T sub O there. That will just cause problems. Okay? All right. So now we're going to go to our energy balance, and it's on the other side. So I'm going to use this one right here. So I'll ask you all to help me. D rho V Cp T minus T reference dt is equal to, and then let me just write out the general equation. Rho I Fi Cp, okay. Rho I Fi Cpi Ti minus T reference minus rho J Fj Cpj. Now Tj minus T reference. I'll leave that there. And then I got my plus or minus Q, and I've got my plus or minus Ws. Okay? So there's my total equation. I'll put brackets on this. All right. So what are some of the assumptions I can make? How am I going to make this monster a little bit more digestible? There's at least 3. Say that again? Okay. So if I look at this problem, what you see here is that, the temperature of the liquid inside the tank is given, the temperature of the flow in is given. There's no surrounding temperature given, right? So in that sense, if there's no surrounding temperature given, we don't know if the surrounding is hotter or colder, so it's pretty ambiguous. So we really can't make any assumptions about how much heat loss from our system to the environment, positive or negative, there is. So because there's no mention or data pertaining to heat losses or gains, whatever it might be, then we have to assume that without that information, we have to assume that Q is equal to 0, or it's negligible, okay? So we're just going to say that that's 0. And, excuse me?
Shaft work is 0.
Okay, why do you say shaft work is equal to 0?
There's no information yet about shaft work.
Excellent. So there's no info about shaft work, so the only assumption we can make is Ws is equal to 0 also. So that's good, that's 0. Okay, so that was 1. There's 2. Okay, what's another good assumption to help us with this equation?
Assume the density and Cp of water is the same.
Okay, so we'll say density and heat capacity of water is a constant with respect to temperature through this range. Okay? All right, so that's nice. You got another one, so now I've got a fourth assumption. And what was the other one that I said a couple pages back that really helps us out a lot?
Constant volume.
Tank is well mixed in overflow condition. Yeah, so V is equal to a constant. We know that because its overflow is given. Dang, y'all are good. 5. What's another good one?
Reference temperature 0.
Yeah, we can do that. Temperature reference equals 0. So that's going to bop a whole bunch of these out. That's great, right? Okay, so now, if all those are true, then what we can do is we can get another, we take our equation out, rho Cp V dt is equal to the rho, the density into the system, times the flow rate in, times the heat capacity. And I'm not putting little i's there because I want them to match these two, because we already said that rho and Cp is constant throughout our system. And then we're going to do a Ti minus, and then I'm going to put a rho. I'm going to omit the J because there's only one flow coming out. I'm going to say F. Oh, I use F sub J. I use F sub 0 there, so I'll put that F sub 0 in. That's a pretty good thing. But Fi and F0 are equal. But they're constants. We know that. And then I need to put T. Now, instead of putting the 0 there, this is where I want to be real clear. There's my T as a function of temperature. And actually, to be more exact in math class and everything, we all get lazy. We don't put the temperature there, but it actually should be there. So what this all means is now we've got this right here, and this is the same variable, okay? And actually, t sub t is going to be our dependent variable, and t is our independent variable. Okay? And it turns out that this is a separable ordinary differential equation. Okay? So it turns out if I ever ask you to solve a ordinary differential equation, I will it better be separable, because I'm not gonna expect you to do any other more advanced techniques than that in this class by hand, not using Laplace transform. So we start at 1:30, right? So it's class ends at 2:20. So we're almost done. Give me one more minute. So let me see here. So I'm gonna do it on this. So now what I like to do is plug in at this point. So density, I'm just going to say, is 1 gram per centimeter cubed. Okay. Heat capacity, that's 1 calorie per gram degrees Celsius. Volume is 4,000 grams. Okay, so I converted the volume to mass, just because I know that 1 milliliter equals 1 gram. So that's dt. Okay, so all that simplifies to 4,000 dt is equal to. Now the other thing I can do is actually, before I even did that, did I miss the heat capacity on this term? I forgot it, right? So tell me those things if you see me do stuff like that. So the heat capacity there goes away, there goes away, and there goes away. And the density goes away here, here, and here, simply by dividing everything by rho and density. So this is still true. This is still fine. 4,000 dt dt. That's equal to the flow in is 2,000. That's 2,000 grams per hour times Ti. Now, what is Ti? Ti is 20 degrees Celsius. And then we've got minus 2,000.
Is Ti not 40?
Oh, Ti is 40, that's right. Yeah. Okay. So basically what we're left with is 4,000 dt equals 80,000 minus 2,000 t. Okay? And the initial condition is t at time equals 0 equals 20 degrees Celsius. Okay? And I got a little sloppy with my units here, but if we go to each one of these terms, they should all equal energy per time. Okay? They should all equal energy per time. Right? And then all you need to do is use the integral tables to solve. Okay. All right. And that's it. Okay? So why don't we all, as part of our homework, just kind of solve that, and then we'll see what that comes out, and we'll talk about that next lecture. All right. This is your next homework. It's got 7 problems. They look like a lot, but a lot of them are just real simple qualitative things to make sure you've read the book and you've thought about process control. Has anybody had success getting the book or no success? You all should be getting the book, and you'll need it for this homework assignment and for reading them. Okay. So I will see you in lab tomorrow, and then Wednesday we'll have class again. All right, we'll pick it up from here.
You got it.